Folks, we've got two more distributions to talk about. The Poisson, which we've already mentioned, but we'll do in a slightly different way, maybe a more convenient way in my opinion, and the beta distribution. By the way, this is the world's tallest known Peruvian man, almost 8 feet tall. Giant of a man. Look at the size of that hand. Wow. So let's look at how we're going to do the Poisson sample from the Poisson distribution, but this time using a discrete cumulative distribution rather than the data analysis tools with a random number generator that we had before. The first thing I want to do is create a cumulative distribution of the Poisson. Remember, we can only create create cumulative distributions for discrete distributions for the purposes of sampling. And we begin our cumulative distribution always with 0. Then we have to calculate probabilities, cumulative probabilities of outcomes. For example, this first probability will be the probability of 0 events occurring in a Poisson distribution with a arrival rate of 7. Let's see how we do that. What we're using here is something called the Poisson distribution, and the arguments of the Poisson distribution are, first of all, the value that we want, 0, that's G6. Q2 is the parameter of the Poisson distribution, or the lambda, average arrival rate, which is 7. And then I place a true here because I want it to be cumulative. So I then put in all my outcome values, 0, 1, 2, 3, all the way down to 21. Why 21? Well, because usually I want to have as many as 3 times the maximum lambda that I'm going to be using. So if I'm using 7, 21 is sufficient. If I'm using 5, 15 is sufficient. Otherwise, we'll wind up bunching up a bunch of outcomes out here. If I'd only selected, let's say, 9, we would bunch up everything from 9 up to, infinity, all in one category. And we don't want that when we spread these things out. So you can see how I've created my cumulative distributions. And then we're going to use a VLOOKUP. The VLOOKUP takes a value, a random number, J6, and is going to go to this table, which is the table given here with cumulative probabilities, and it's going to return the second column value. And just as before, if I get a value, for example, of 0.053, let's see if we can find that on the table. Well, we don't see it directly, but we know it's between 0.029 and 0.018, and therefore it's going to return the top value in that bracket. It's going to return 3. So here's another one, 94945. Where is that in our table? 94945 is someplace between here and here, so it's going to return a 12. Okay, so now I'm going to take this value that I've just determined, this looked up Poisson random variable, 12 arrivals, and then I'm going to create a data table to create many values and plot them to see what this distribution looks like. So here I've got my frequency distribution, and you can see what this distribution looks like of a lambda 7 for my Poisson. If I hit F9, that will recalculate, and you can see that the general shape will remain the same. The table or the graphs will change slowly. So I hit it again. We make some changes, and there you see it. Kind of a central tendency centered around 7 because that's the average arrival rate. But some values way out here. For example, this one had one that was 16. Let's play with it a little bit and see if we get anything larger than 21. There's 3 14s that occurred. There's a 16 again, another 16, a 14, 16, 2 16s, 14, 2/15. You can see that our selection of 21 was a very safe bet for us, but and the general shape of this distribution remains the same. All right, that's how we sample from this distribution. So in the use in a spreadsheet, in a Monte Carlo simulation, I would create this table someplace, and I would use the VLOOKUP with a random number to go over here and sample from this table for a lambda of 7 and return a value of sampled Poisson outcomes, in this case 12. That's the conclusion of the Poisson as a discrete.